Today I'm going to talk about dynamics and chaos. It's a bit of a silly topic to choose for one of these seminars because it's an entire branch of modern mathematics, so can't really say that much important stuff about it in a short period of time, but I'm going to try. I'm just going to go through and give some nice examples and some reasons why we're interested in this sort of thing. Well, that's a shame. It all starts with the three-body problem. As I'm sure most of you are aware what the three-body problem is. You have three bodies in space, only physicists are original at naming things: the sun, the moon, and Earth. And given an algebraic approach, like using algebra and differentiation and integration, you can't solve this system for all time. You can't create systems with solutions which tell you the explicit paths of where everything's going to be realistically. It's not a possible thing to do. It's just unreasonable. So Henry Poincare in the late 1800s devised a solution to this. He focused on asking a different kind of question because it turned out that the problem with the three-body problem wasn't that we had an impossible question, it's that we were asking the wrong question. It's that instead of asking about whether the Earth, the Moon, and the Sun will collide, we were asking about whether it'd be every single time. Instead of wondering about the long-term solutions and the implications of the system, we were more concerned with the specifics, and we threw away the geometry of the system in those cases. So it's just a new approach to solving new being 100 years old. So that's really new for mathematics, and it's an entirely different focus. It takes away from just plug and play algebra and into the realm of geometry. So let's start off with an example of a simple equation. This is the logistic equation. It models population with n dot being the rate of population growth of a species, r being a population growth coefficient, n being the population of the system, and k being a carrying capacity, which represents the maximum eventual growth of a system, of a biological population. And instead of directly algebraically solving this, we're going to look at what happens when we plot n dot versus n. We see that when we plot n dot versus n, that we get a very specific, very strange solution. We see that over time, as n increases, we reach a maximum threshold to which the population will grow no more past the lines of the axis of the equation, obviously. And so we reach that intersection at 3, and we have no more growth in the system. That's the maximum biological limit for this system. It won't grow any more past this point. So to further understand the system, we think about what's happening over time. And we see that with those helpful arrows, that while that indicates the direction of what's happening to the population at that time. In the first arrow, for any population in that area, because it's a positive value of d and dt, it's increasing over time. It's going to grow onwards. It's going to increase in population, so it goes forward. And on the other side, we have a negative value of d and dt, so the population is going to decrease. And in between the two of those, we have a point that we will refer to as a fixed point. And at this point, because one side's pressuring it there, one side's pressuring it forward, and the other side's pressuring it back, that's where the system is naturally going to fall. Like, eventually it'll come to that equilibrium. It'll balance out, and the population will essentially stagnate at that level. And also we see that there's another fixed point at 0 population. Strangely enough, if you examine a biological population that has nobody in it, it stays at nobody forever. The wonderful world of mathematics. Who would know? But so we're really interested in this because we've essentially found a solution to, well, a solution to what will happen to this system of biological populations without really doing any maths, which is awfully intriguing. Like, we're not doing any traditional maths. We've plotted a graph and then we've looked at it and we've been like, oh yeah, goes that way, goes that way. Well, what do we want to do? So we see that the behavior follows a very, very clear geometric form. It's very specific. So if we look back at this, we know that it's partitioned into regions for which we have growing population and shrinking population and standard population. Like, we're thinking about the intrinsic geometry of the scenario a lot more instead of the equations themselves and solving the equations. So this is a really, really simple scenario. I'm sure you could all figure it out without doing any of this. But now we wish to extend it to a more complicated problems, because this is just, obviously too simple. This is another system that also represents biological growth, just a more complicated form of biological growth. And we see clearly defined regions of this point here pushing away, and this point here pushing away, and this point here pushing away. And so if it's on any of these points, it'll stay here forever. But if it's here, it'll shoot off to negative infinity. If it's here, it'll go to here, here it'll go to here, and here it'll shoot off to positive infinity, which is an interesting scenario, but that's pretty much what we expect. But now we're going to start varying some of the parameters and see what happens if we change some of the initial conditions of the scenario we've put forth here. And so we shrink it in, and we've gone. So if we look at this point here, this is at 0, right? And this one's at -1. And by varying the parameters, we've created a scenario where this is at 0 and this is at 0.5. So the fixed point that was over here has moved through the system somehow. That you don't know, but I guess I'll tell you. But somehow it's moved through the system, and we've got a completely, well, we've got the same setup, but that's just because of this equation. So what happens in the case in between? Well, we have this weird half-stable point where it shoots off to infinity in this direction, but from this direction it's attractive. Like, it's not like the other scenario at all. And this coalescing of points, essentially this collision of points into a new point, is called a bifurcation. These play a massive role in understanding our understanding of how these systems work and how these systems change for different parameters. And we've got 3 normal kinds of bifurcations. There are more, but these are the basic ones. So when a stable and unstable point annihilate. So stable is when it's drawing things in, unstable is when it's pushing things away. Transcritical is when the fixed points exchange stability, which is what we had just before. If you see the 2 fixed points change the stability they had, because one of them is moved along the axis and they just swap their stabilities. And we also have a pitchfork, which will turn a single point into multiple points. Yeah, obviously, if we want this approach to be of any use at all, we need more than one dimension. One-dimensional model would not be very useful for pretty much anything at all. So to do this, we use an approach where we analyze the eigenvalues of the Jacobian, and that corresponds to various phase portraits. Now, I guess I've got some explaining to it. I should have included this, but the Jacobian matrix, so if we have a 2-dimensional system defined by 2 equations, so f is equal to f of x, g is equal to g of x. The Jacobian is the matrix defined. The Jacobian is the matrix defined by df x and when we think about it, the fact that our system is defined in terms we can find from that matrix makes a lot of sense, because if we look back at these ones, what we're essentially doing every single time, although we're not doing it explicitly, we're looking at the rate of change of the system. We're looking at the rate of change of each of the components, and essentially the Jacobian is allowing us to do that in more than one dimension. So by extending this kind of analysis to, by extending it to a Jacobian, we're essentially doing the same thing we were doing before, except now we're actually doing it with maths. So we use this to form what we call phase portraits. Now, phase portraits are essentially a two-dimensional description of a system that sort of like a map, essentially. And depending on where you start on that map, you'll move around according to the way the picture's drawn. Now, this sounds a bit weird, but these are the kinds of things that you can get moved around by. Depending on the eigenvalues of your Jacobian, your corresponding pattern, essentially, arises from these. You can see here you've got points which everything attracts to in 2 dimensions, or points that only have attraction in 1 dimension, or points that attract here and then repel along this axis. And this one attracts everywhere, repels everywhere. You've got weird spirals which over time will spiral into the center, and complete centers which oscillate around a point but never really get closer. They're a perfect center. They just sit there and oscillate around a point. Now, this is a lot of information taken at once, so I'm going to use an example from Strogatz, which is a fantastic textbook. We have the love affair between Romeo and Juliet being modelled by dynamical systems, where R dot is Romeo's change in love for Juliet, and J dot is Juliet's change in love for Romeo. And Romeo is a lover. When Romeo's in love, he gets more in love. He feeds off his own love. He's just infatuated. It's just his personality. And when Juliet shows signs of affection, Romeo, he starts to go crazy. He's just uncontrollable. Whereas Juliet is the complete opposite. If Juliet thinks she likes Romeo, she instantly likes him less, which is woman, you need to understand. And if Romeo likes her, again, she likes him less. I mean, it's foreign to me, but the maths, you can't argue with the maths. And what you get are these really weird solutions. So this is a particular solution, given the right infatuation constants, I think I'll call them, between Romeo and Juliet. As you can see, the same constant is used between each of the relations to simplify the system. So given the right infatuation constants, you get this, which is a plot of how much Romeo loves Juliet versus how much Juliet loves Romeo. And I mean, it just goes around in circles forever. This is not a good situation to be in. You will be in true love 1/4 of the time. But you also be in true hate 1/4 of the time, and some half-baked combination half the time. So not really an ideal situation. We also have this situation, which is some very strange movement. It depends entirely on what they first say when they meet, their initial conditions. Like, first impressions really matter. I mean, this is just mathematics telling us what conventional wisdom has told us for a long time. We see that you can shoot off to infinity this direction, but in both these models, Juliet isn't really that happy in this case. Like, Romeo, since they're both shooting off like this, Romeo is just either falling completely in love just absolutely hates her. But she's just kind of neutral either way. They're kind of can't really make up her mind. She just doesn't care, which is pretty weird. And this is a pretty interesting scenario as well. A pretty bad one. The only cases that arise from this scenario is Romeo hating her while Juliet loves him, and Juliet hating him while Romeo loves her. So can't really win with that one. So yeah, first impressions really matter. What are some other systems where this kind of approach is really useful to understanding what's going on? Well, it's really useful in chemistry. Chemical balances and chemical mixing plays a major role in this. The competitive biological models, like different population models competing against each other, are really easily modeled by this sort of thing. Geoffrey West is a very interesting man. He was a physicist. Now he's kind of a mathematician. What he does is he models cities and corporations and compares them to biological organisms. And he does that all under this kind of approach. And as we all know, corporations eventually die out, and cities don't. Like the cities that have been here for a long time are still here. The cities from ancient times that have been here are still there. Nearly all of them are. Whereas there's not really any corporations around today that are over 200 years old. And he aims to try and explain this thing, these kind of phenomena, using this kind of approach. And it's extremely interesting. And he did a fantastic talk, which I'll probably link on the Facebook page after this seminar. It's also really useful for genes and triggering effects. Like there are a lot of genetic preliminary effects you have, which are then triggered by an environmental effect, like a certain chemical getting into your bloodstream, or reaching a certain amount of hormone balance or whatever might make your hair go orange or something. I'm not quite sure. I'm not a biologist, but apparently it's really useful for athletic performance. I don't know, like studying athletic performance, understanding how bodies work, really useful. I don't know how, but apparently it is. And basically everything that can be modeled with a time dependence and seen as a flow, a complex system, or things networking together that can be thought of with flows, this type of analysis is extremely useful for. Chaos. Oh. This is Edward Lorenz. He's the father of modern chaos. The story goes that he was studying atmospheric convection on what was one of the top-of-the-line computers in 1961, which was, wow, really amazing stuff. He had a model which was running in 6 decimal places. It was doing its calculations to a whopping 6 decimal places, but it was only giving him output to 3 decimal places. And since he was on such a whopping beast of a machine, he decided it'd be easier if he just ran the model halfway, got out the parameters, and then put the parameters back into the model. But because of the difference in decimal places, he was getting ridiculously different answers to what he was getting from his initial runs. So his results would diverge massively from what he initially got. And he thought that was awesome. After, figuring out that it wasn't his fault, he thought it was awesome. Initially, he probably was pretty upset. And so he went on to define chaos, but I'm going to use this definition. So chaos is aperiodic long-term behavior in a deterministic system which exhibits sensitive dependence on initial conditions, which is a really big mouthful. So aperiodic long-term behavior means that it doesn't settle down to fixed points or orbits in the traditional sense. like it doesn't follow like a periodic behavior essentially. Deterministic, I'm sure you're all familiar with. It just means that the whole system can be predicted from initial conditions. There's no randomness in place. There's no noise that's throwing everything off kilter. It's just 100% predictable. And it needs to have a really high dependence on initial conditions. Slightly different initial conditions lead to very different results. And I think this is best summarized by Lorenz's own definition of chaos. Chaos, when the present determines the future, but the approximate present does not approximately determine the future. And essentially, the point he's trying to get across there is, if you know everything, you will know everything to come. But if you don't know everything, good luck with that. So he proposed the butterfly effect. I'm sure you're all familiar with it. As a consequence of chaos, hurricane formation may or may not depend on if a butterfly flapped its wings several weeks earlier. So it's a strange idea, the idea that their sensitivity to initial conditions is so high that one butterfly on another continent flapping its wings can change the air currents of the Earth so much that a whole tornado happens or doesn't happen. But I guess that's mainly because as humans we don't really think of small things coming together to make giant effects. We kind of take in our stride and think it's all us and everything we do is responsible for everything that happens. And I guess to some degree it is, but it's a bit more diverse than that. But it is an indicator of how extreme the sensitivity to initial conditions can be in a chaotic system. Oh, it's a shame that didn't work. Let's see if I can. Nah. Okay, well, that's supposed to be a GIF of a double pendulum, but it's not working properly. That's a shame. I'll talk about this instead. This is a chaotic water wheel. Essentially, the premise is all of these cups have holes in the bottom, big holes, I guess. And those arrows are essentially sources of water. Now, over time, this bucket, imagine this is not moving. This cup will fill up with water enough so that it starts moving the wheel. And hopefully you set it up so it moves it enough so the next cup starts filling up with water. And the next cup, and the next cup, and then it starts spinning. And over time, you lose track of what way it starts to spin in different directions because the flow of water starts to become completely unpredictable, and there'll be, as like all the cups on this side have all of a sudden become out of water, then it'll start spinning this direction, and then as they start to empty, they'll start spinning this direction. It's a very unpredictable system. It identifies strongly what a chaotic system is, and it's a shame that GIF isn't working. So Lorenz's original study led to the discovery of a chaotic solution to the system he was looking at called the Lorentz attractor. This is a type of object called a strange attractor. It's kind of like fixed points in the sense that it indicates the trajectories of the motion, but it's a bigger structure than that. It's not like something directly goes somewhere. It's an entire structure of trajectories that move in all sorts of random three-dimensional, well, not random, but three-dimensional directions. So this is what Lorentz attractors look like. And I don't know if you can see it very well, but right here is where all the initial conditions are very, very tightly packed, like all covered by my finger there. And then the different initial conditions lead to different developments over time in this one here. And then they spread out to this thing, all starting at the same time and having the same time run. And eventually they lead to this solution, all from the very insignificant difference, well, traditionally insignificant difference in initial conditions here, which is just astounding. That's the underpinning of chaos right there. Now, fractals play a major role in understanding the geometry of the strange attractor. They I don't really understand this properly myself, so I'm not going to go into too much depth about this, but the actual geometry of the strange attractor itself means it is a fractal and it has fractal geometry about it. And so this is the Mandelbrot set, the most famous fractal. It looks really nice. Well, it does. I mean, it's just a repeating pattern essentially. Not all fractals have to be repeating patterns, but in this case, this one is. My favourite fractal is the Koch curve, the von Koch curve. Essentially, it starts off with a line. So you have a line, and so you got your big line, and then you take out the middle third of it. Don't want that. Replace it with a hill, and then you take out the middle third of each of those parts, and you replace them with hills. And you repeat this process for infinite recurrences, and what you get is this, a seemingly strange shape that actually infinitely repeats itself. It's just simple, using the same pattern over and over again. You get the very, very diverged 3 points there from the initial 3, and each increment will be small. This is a fractal. It's a particular type of cauliflower, although it looks more like broccoli, I guess. But it is an example of fractal growth from nature, and it's probably something that's been environmentally beneficial for the plant to take as a evolutionary trait, because it's a very spatially compact sort of growth. In fact, fractals are so spatially compact that there are now people in solid state and condensed matter physics examining whether they are the best forms of growing your connectors between various different solid state materials. This is a shame because this was a really good image. It was showing how you can use fractals to create essentially backgrounds, like all of the early computer imagery from like the 50s, not from the 50s, from like the 70s to the 90s was done using fractal technology. Essentially, you draw an image and then you can make really high definition green screen images by placing the same reoccurring growth. And it's not computationally intensive either, because you're only executing the same command every time. So you can easily recreate these vastly more complex images than the underlying principles. And I would finally like to talk about something really useful that comes out of chaos. Chaotic encryption. You can transmit messages masked in chaos. So essentially, you've got a business partner that needs to, you need to transmit some hidden message that no one else is going to pick up on, that anyone who intercepts halfway through is going to be blocked. And what you do is you have a very specific electronic circuit which generates which adds chaotic noise to behind your original message. And then this chaotic noise can then be decoded by your friend using very precise equipment on the other end, which follows the exact same methodology as your equipment. And then they can retract the original, they can retrieve the original signal you sent. And anyone who intercepts it halfway doesn't know the configuration of your chaotic setup, so they just get noise. There's no way they can get rid, but it's such an unpredictable, because the fundamental nature of chaos is that it looks unpredictable, but it's predictable. To anyone intercepting it, it's unpredictable. They don't know the underlying structure.
Well, we can't rely on them not working out the equipment that you've used because they put in a spy to your organisation. You're still surely going to have that a brute search for through all configurations. Is it going to work?
Well, the brute force search doesn't really work, but if you do have a spy in your agency that's going to find out your equipment, the problem isn't with the message you're sending in yourself. It's probably your organization's fault. I mean, you just don't...
The fact is that whenever crypto systems have been used, where it's simply the secrecy of the cryptographic algorithm and not the sort of specific keys you're using, there's always eventually fail.
The algorithm is a key in this sense. Like, you can change, as long as it's a chaotic algorithm, you don't have to specify what one. As long as you can create it with an electrical circuitry, you can do this. So any chaotic system that you discover with very particular solutions, any chaotic system that's solved essentially, you can do this using this technique. And this was actually successfully demonstrated in 1992 when a MIT student in his free time made a radio, essentially. And what he did is he went to his class and he demonstrated in front of his class. He first played some Mariah Carey through his speaker, and then he plugged in his electrical circuitry that he had built in his own time, his particular circuitry, which encrypted and masks this message. And by playing through that, everyone heard was noise. And apparently, one of the students remarked, "I don't think this is much different from the first play. I can't really tell." So, I'm not a big fan of Mariah Carey. But then he had a second radio transceiver, which he then hooked up to a decryption software, a decryption hardware, a decryption circuit he had, which received the message and then played back to the entire class perfectly Mariah Carey, which is absolutely fantastic.
Mariah Carey on the spot.
Not so much in Mariah Carey.
Yes, question on that. Given the tolerances on most electrical components, you're going to need some quite precise stuff that you can't just buy from a hardware store.
Yes, well, that is true. From what I gather, the way he developed it is he used a very precise electronic setup that he basically handpicked everything perfectly so that it would fit the circuit exactly. And if he was to change his chaotic encryption, he'd have to do that again in a different way, because essentially the mathematics is run through by the electronic circuitry. So it is very, very bad in that regard. It doesn't really have much adaptability to electrical software. It does require electrical hardware. It does require very, very precise components.
Yeah, mathematically, what we then really want is a way to generate a large number of such circuits that could be used and rapidly interchanged. So, do you know anything about that, or?
No, I only know a little bit about this stuff myself. It is pretty complex stuff, as I said before. This is something that was figured out in 1992. So it is fairly new. I don't know if there's been much done in the way of progressing it. I haven't seen anything since then. So, well, I've seen things since then, but I haven't seen anything that happened since then. Any other questions?
With this chaotic encryption, how undecipherable is the message in terms of why could someone not just run it through a system and leave it running for weeks and weeks and weeks until it eventually...
Because the nature of chaotic systems... Essentially what you're doing is... So here's a frequency band and say this far is human hearing. And say you want to send a voice message, like your Mariah Carey. It'll probably operate like this. And what chaotic encryption ends up doing to the system is sending a wave packet that looks like this. it's just completely unfeasible to attempt to extract the initial results from it. But because it's built on a very, any attempt to try and solve it requires the knowledge of the initial conditions used to establish the encryption, and because chaotic systems are so incredibly sensitive to initial conditions, any close approach, even a really close approach, even like as Lauren said, approximately knowing the present doesn't approximately know the future. So any even you can't even tell if you're getting close is the problem. Like there's no way of knowing.
If I may make a comment here, a perfect system would add an entirely random component, and as then it could be anything, you could have sent anything, as there'd be some random component that when added to it would give you the wanted result. Now here, random's problematic because you've got to send the other person a secret description of the said random thing. So you're here using something pseudo-random, which is the chaotic system, and the question is then, how many sort of different chaotic systems could you feasibly be able to sort of be switching in and out, that therefore anyone who wanted to decrypt it would have to run through all those systems and all those circuits?
I feel that's the reason why it hasn't really been just very developed at the moment, because, well, at least to date, because it requires, if it was developed initially, then it would be a very easy decrypt.